In the series of lantern slides illustrating the formation of the fourth bridge, the intention is to show, first, by means of skeleton sketches, the nature and qualities of the design and the foundations, and then, by photographs of the superstructure at different parts, and from various positions, to remark upon the progress made from time to time and the manner of building adopted, till finally we reach the completed viaduct, a view of which fitly completes the selection. The decision to build a bridge connecting Edinburgh directly with the north, has been the result of the keen competition between the two leading Scottish railways along with their several allies, the English trunk lines. This is by no means a new idea however, for at the beginning of this century, a company was attempted to be floated in Edinburgh to build a viaduct on the exact site of the present gigantic structure. The chances for the company being a paying one, may be imagined when it is stated that the capital of the company was to be £150,000, whereas the present bridge, constructed with the aid of the best and latest inventions in material and labor-saving tools, has cost, with approaches, from first to last cost some £3.5 million. The fourth being exceedingly deep, it was resolved to bridge it at Queensferry, opposite the island of Inchgarvie, so as to take advantage of it for the foundations of the central pier. The depth of water in the divisions of the fourth on each side, 200 feet, made it necessary that the adjacent pier should be close to the land on each bank, and, as the Board of Trade stipulated that the shipping plying up and down the estuary should be in no way hampered, the spans had to provide sufficient headway to permit the tallest masted vessel afloat to pass through. The height fixed on, 150 feet clear of the water, amply allows of this, while two giant strides, of 1,710 feet each, from Inchgarvie to the Fife and Mid Lothian sides, made it possible to found the side cantilevers in comparatively shallow water. This shows a cross-section at one of the three central piers. These three piers are all similar in cross-section, but the middle, or Inchgarvie, pier is wider measuring along the bridge. The two outer piers being 145 feet each along the bridge, while the center pier is 260 feet. The width of the piers across the bridge, as shown on the screen, is, at the base, 120 feet, and narrows to 33 feet at the top. The height of the steelwork is 333 feet, or 360 feet above the high water mark of ordinary spring tides, and, as the deepest caisson reaches down to 90 feet below that mark, the maximum height, measured from the foundations, is 450 feet. The decrease in width as the height increases, is considerable, and is intended to enable the fabric to better withstand lateral wind pressure. This power of inertia is increased by enlarging the base as compared with the area of the superstructure, a factory chimney stalk and one of the Egyptian pyramids being good examples of buildings of the least suited and the best suited forms of construction for weathering every gale. That mistakes have been made in planning bridges in similar exposed situations by not reckoning sufficiently with this sometimes immense force, will be understood by all who remember the disastrous end of the first Tay Bridge, which was blown down in December, 1879. For comparison with the present fourth bridge, a skeleton cross-section of the ill-fated Tay Bridge is shown, drawn to the same scale. It will be seen that the fourth bridge, with its legs well parted at the feet, has a much more stable appearance than the upright columns of the Tay Bridge, and the designers affirm that each pier, although it has to stand the pressure of the wind on a length of about 1/3 of a mile of superstructure, will safely bear a cyclonic pressure of 56 pounds per inch blowing eastward on one of its cantilever arms and, simultaneously, westward on the other. Such a test it is never likely to undergo, as these conditions are far more severe than anything recorded in our country, for, during the storm of unprecedented severity to which the old Tay Bridge succumbed, the highest pressure reached was estimated by experts at 30 pounds per square inch. As may be seen on this plan, the cantilevers taper, not only from the base to the top of the piers, but also from the base of the pier to the outer end of the lower member of each cantilever arm, and in a much less degree to the extremities of the top members. As the strains on the several sections of the cantilever arms decrease in intensity as we get further from the piers, so the girders and tubes are made proportionately lighter, to economize material, and ensure that, as nearly as possible, all the ironwork shall be equally effective. In the two center spans, the ends of the cantilevers are connected by lattice girders 350 feet long, and weighing 800 tons each. The railway runs between, and level with the bottom of, these girders, which are fastened at one end only, in order to allow of expansion and contraction from change of temperature. The total change of length provided for on the bridge is 7 feet, or at the rate of 1 inch in every 100 feet. The diagram below shows how 2 Eiffel Towers can be fitted into one of the 4th bridge cantilevers. The foundations for the 3 cantilever fabrics are 3 sets or clusters, of 4 columns each. These columns are formed of a lower iron tube or caisson, which is sunk into the ground and then filled with concrete, and above the caisson, on the top of the concrete, masonry is built 27 feet high, to bring the height up to the level from which the lower boom of the cantilever springs. These caissons were made in Glasgow, and fitted together in the bridge works at Queensferry. When empty, each weighed about 400 tons, and when filled with concrete should weigh about 5,000 tons. The caisson consists of a tube within a tube, the outer one being 70 feet diameter at the bottom, and 60 feet diameter at the top. 7 feet from the lower or cutting edge an airtight floor was built, beneath which, when sunk in position, excavation was carried on. The launching of these caissons was sometimes attended by a good deal of ceremonial, and was held as a general holiday by the workmen and local inhabitants generally. Many distinguished visitors took part in the proceedings on these auspicious occasions, and, in the usual manner, broke a bottle of wine for luck by throwing it against the side of the tub-like vessel as it took the water. The caisson, having been safely launched, was towed out to its ultimate destination, where, after having had a temporary additional ring of plates fastened onto the top of the caisson, to keep out the water at high tide, 2,000 tons of concrete were filled in, causing the whole gasometer-like mass to settle down in the position chosen for it. An accident, which caused great delay, happened to one of the caissons while floating near its position, for, after being towed out, at low water it stuck in the mud so fast that the lifting tendency of the returning tide was insufficient to float it before the water rose to the level of the upper edge of the caisson, which then of course became quickly filled, and lost all further inclination to even attempt to float until after 9 months of labor and ingenuity, when, by transforming the submerged caisson into a watertight barrel, and pumping it dry, it resumed the status quo once more. On the top of the permanent caisson a platform was laid for mixing concrete, and on the top of the temporary portion a platform was provided for general purposes. As has already been mentioned, each caisson was provided with an iron floor 7 feet from the bottom. This airtight diaphragm served to divide it into 2 separate chambers, the lower of which was, when in the water, simply a huge diving bell, and the men who entered it to dig out the foundations did so through a vertical shaft with an airtight lock at the top. The air pumped into them under pressure, as will be explained afterwards, drove the water down in the chamber, and enabled the men to breathe. The materials excavated and concrete were passed in and out through traps working on a similar principle. As for every 32 feet that we descend below the water level we require an additional pressure of 15 pounds to the square inch to force the water down to that level. It will be apparent that before the maximum depth attained was reached, the workmen in their underground cell were laboring under very great disadvantages. The pressure occasionally reached as high as 48 pounds to the square inch when the bed of the river had an unusual depth of thin mud. For this submarine work, men had to be specially brought from Belgium, where large dock constructions had necessitated the training of great numbers of men to toil under similar conditions. During excavation the interior of the excavating chamber was lit by electricity, and the labor was greatly facilitated by Mr. Errol's invention of a special mechanical digger, worked by hydraulic power. The chamber was occupied on the average by about 30 workmen at a time, and many visitors went through the disagreeable experience of swallowing compressed air and descending the shaft to the mine below. An amusing anecdote is related of a gentleman who carried a flask of spirits down with him, and broached it before ascending again. It took him so long to get to the top of the ladder that, when in the airtight chamber, he produced the pocket pistol once more, but on stepping into the open air it burst like a hand grenade, to his great consternation, the reason being, of course, that the pressure outside the bottle was insufficient to counteract the compressed air that he had admitted. When the caisson had reached its proper depth in the boulder clay, the air chamber was filled with concrete well packed, as was also the upper body of the caisson. An addition of stonework, 27 feet high, brought the column up to the level for laying the steel plate for carrying the bridge. This plate was fastened down by 48 steel bolts, each 2.5 inches in diameter, and piercing the stonework from Top to bottom. Difficulty was experienced in keeping the caisson upright in several cases where the foundations were on a sloping rocky bottom, as it became necessary that the outer edge should be temporarily supported on heaps of sandbags and banks of concrete placed by divers. The rock being gradually blasted away by dynamite, the temporary supports were lowered and adjusted as the caisson sank and secured for itself a solid and level rock foundation. It is computed that the greatest weight on the bottom of one of the caisson will not exceed 5 tons per square foot. On top of the masonry 2 steel bed plates are fastened by means of the 24 bolts already referred to. The lower plate weighs 40 tons, and is rigidly attached. The holes in the upper steel bed plate, through which pass the tops of the huge bolts, are not circular but oval. This allows the whole superincumbent mass to move bodily to the extent of a few inches in a direction across the river when expansion from heat occurs. In the case of wind, the heads of the bolts would prevent any tendency to rising, so that, paradoxically, because the bridge is not secured, but allowed freely to accommodate itself, it is more secure than if it had been rigidly attached to the piers. The various tubes and girders that spring from each pier are all attached to a sort of compound socket or joint known as the skewback, the base of which is the upper bed plate already mentioned. The skewback is the focus at which the principal thrusts in the bridge converge. It is situated nearly in the center of the pier, and its complicated construction may be surmised when it is known that from it spring 5 girders and 5 tubes, 3 of the latter being 12 feet in diameter and 2 8 feet. Each upright column, 340 feet high, is 12 feet in diameter throughout, and is built of steel plates, gradually diminishing in thickness to the top. The outside shell of the tubes and columns is connected transversely in the interior by a network of braces. The outside plates were bent and fitted, and the rivet holes drilled in the works on shore, and were then, one by one, riveted together on the pier in their respective places. The riveting was all done by hydraulic power, and unattended by noise, so that the impression conveyed was, that the fabric was, as it were, growing from day to day, each addition being entirely unheralded by the usual din of the boilermaker's hammer. The gradual heightening of the columns by the addition of plates was done from a platform which was supported by lifting girders projecting through, and fastened to, the part already executed, and they were raised as required, also by hydraulic power. The necessary riveting was performed in a circular cage surrounded by wire netting, attached by iron straps to the lifting girders just mentioned. Although the columns are vertical when seen from up or down the river, they converge from 120 feet apart at the base to 33 feet at the top when seen from either end of the bridge, for reasons connected with the stability of the structure, as has already been explained. From the top of these columns, on a clear day, a beautiful view is obtained for many miles in every direction. The hydraulic lifts used for raising the workmen and materials were, during the period of construction, available to make the ascent easy for privileged sightseers. A strong staircase, which zigzags up the diagonal bracing to the top, may still be ascended by those of an energetic disposition, as it formerly was by many who placed not their faith in hydraulic lifts. In the cantilever arms the bottom members are the tubes that spring outward from the skewback, and, although the general impression conveyed by them is that of a curved arch, closer inspection shows that each of the 6 lengths of which they are composed is perfectly straight, and is of gradually smaller diameter as the outer end of each arm is approached. For example, the first length begins at 12 feet diameter, the next at 10 feet 6 inches, and so on, so that the real shape is something like a long telescope drawn out and slightly bent at the end of each joint. The total projection of the points of these bottom members is 680 feet from the center of the skewback, where they are 120 feet apart, and at the point they approach to within 22 feet of each other. The top members are the girders which, having connected the 2 vertical columns at the top, slant downward and outward to the extremity of the arm, and at the same time converge slightly, from 33 to 22 feet apart. Like the bottom members, these girders gradually decrease in section as they recede from the pier, and as they are therefore built on what may be called a compound slant as well as tapering, the difficulties to be overcome in fitting them and their connections together can hardly be realized by anyone who has not been engaged in such work. There are 6 tubular struts to each bottom member, each decreasing in caliber and length, and increasing in slant or rake as they approach the center of the span. The length of the shortest is 75 feet, that of the longest 340 feet. In section they are like a circle with flattened sides. the flat parts being utilized to effect junctions with the girders that are fastened to them. The 6 ties which depend from each top member are attached to the bottom member at each point where the corresponding next strut slants upward from it, these junctions being formed by modified skewbacks. As each pair of ties and struts crosses approximately at their centers and traverses the same distance horizontally, they form, when viewed from the side, a series of diamond-shaped openings, gradually decreasing in size and varied in shape, which tends to break that monotony of angle which is so noticeable and disagreeable to the eye in very many iron bridges and structures. The ties, like the top members, consist of rectangular lattice girders, and are of lighter construction as they get shorter. To further support the great weight of tube in the lower member, it is held up by a vertical tie connecting it at the center of each bay with the intersection of the tie and strut overhead. These vertical ties also support the viaduct girders, which thread their way through the network of steel, each girder diminishing in depth as the distance between its supports becomes less. The view projected on the screen shows the undertaking as it appeared in May, 1889, about 6.5 years after first breaking ground, and within measurable distance of the grand consummation. An idea of the vast size of the work, both in its details and as a whole, may be tolerably grasped by observing the insect-like appearance presented by one or two of the men, one to whose fearless and patient toil we owe the uprearing of this latest wonder of the world. The method of extending the several limbs of the bridge can be seen by noticing the platform at the outer extremity of each unfinished tube and girder. Each is supplied with steam crane, and also with hydraulic riveters and rivet heating furnaces. The method pursued is as follows. Full-size drawings are made of each separate plate and bar in the drawing office, and the steel being adjusted exactly to these in the works, is then, also in the works, accurately fitted together, the rivet holes bored and each part marked, taken apart, and stored till required. It is then conveyed out along the pier constructed at Queensferry, or out in boats, till beneath the position it is to occupy. The steam crane tackle hoists it to the platform, where it is refitted together, and the requisite rivets heated, and, one by one, inserted in the holes bored for them, when the 2 arms of the hydraulic riveter, placed opposite each end of the rivets, close in a silent but resistless embrace, which molds the flat point of the rivet into a semicircular head. At first a good many accidents were caused by rivets being allowed to drop from those aerial platforms, as, by the time they reached the water level or lower staging, their velocity resembled that of a bullet, but, afterwards, this was prevented by hanging a wire netting immediately beneath these platforms to intercept them. In all about 6 million rivets were used, and those whose talents lie in that direction have made curious calculations, as for example, that they would reach when placed end to end, a length of 380 miles. Frequently in building out long girders and tubes in advance of the rest of the structure, temporary supporting girders, cables, or chains had to be attached, to keep their progress in correct line, until they reached the next point of support. When finished, these cantilever arms are, Mr. Baker, one of the designers, affirms, strong enough to support 6 of the largest ironclads suspended from their extremities. It will be noticed that the 2 arms of the central cantilever are equally weighted, each having to support 1/2 the burden of the central girder extending from it, but apparently those of the Fife and Queensferry cantilevers, while built almost symmetrically, are not in an equally balanced state, for they have no girders or half-girders to keep down the shore ends. The absence of this is compensated for, and equilibrium re-established by making these outside arms 10 feet longer and, in addition, by holding them down by means of huge bolts built into the masonry, so contrived as to admit the sliding movement caused by the contraction and expansion of the bridge, but resisting vertical movement as they are anchored down to a mass weighing over 1,000 tons. Provision has had to be made at the extremity of each cantilever arm for the safe adjustment of the rails, when, owing to expansion caused by a great rise in temperature, the ends of 2 adjacent arms have moved nearer to each other by say 1 foot. To lay rails in the ordinary manner at these points, where the whole expansion due to one arch is concentrated, would only bring about consequences similar to what took place in the first railways, when the science of rail laying was not understood. At that time the rails were laid butting close against each other, with the result that on a warm day, as there was no provision made for expansion longitudinally, the rails were forced up into a series of arches, with their chairs and sleepers hanging to them. In the 4th bridge the expansion is allowed for, at the points named, by making the joints on a long slant, each end forming a pointed wedge, which is pushed by elongation past the other point, so that the fact of these taper-pointed rails projecting a few inches more or less past each middle dot other will make no difference to the continuity of the rails or their fitness to allow of railway traffic being conducted smoothly over them. The interest and novelty of the fourth bridge undoubtedly centers in the three great cantilevers, but the approach viaducts at each end are also considerable undertakings, and no account of the bridge would be complete without mention being made of them. The approach viaduct on the Fife side has 5 spans, while that at the Queen's Ferry end has 10. These spans are each 168 feet from center to center of piers, and the girders, which are of steel, and 22 feet 6 inches in depth, are of the ordinary lattice bar type. The peculiarity in the method of their erection lies in that the masonry piers were not first erected, entailing difficulty in transporting building material, and the girders afterwards built across them, which, as they are about 130 feet above water level, would have necessitated complex and expensive scaffolding. The girders were built on the piers as soon as these were raised a sufficient height above the ground. The hydraulic power and so many applications of which had been used in constructing the bridge, was taken advantage of to raise the girders above the stonework, so as to allow of additional courses of masonry being laid, and the operation repeated till the full height was attained. Inside the girders a temporary floor and tramway was laid, along which were run the wagons, in which the granite blocks for the piers arrived, depositing their load at the several points, as required, the wagons having first been middle dot hoisted by steam power to the level reached by the girder. Considering the amount of work to be accomplished, the time occupied in building these stone piers, from first lift to last, namely 15 months, must be allowed to have been very short. The lifting of the girders by the hydraulic jacks occupied, at first, almost a day, but, as experience developed, and better methods were applied, this time was shortened to a period of less than 4 hours, even when a row of 10 spans had to be elevated simultaneously. Beyond what has been remarked, there is no special peculiarity about these approach viaducts unless it be their exceptional height and the remarkable dimensions of the terminal piers. At the foundations these measure 100 feet by 50 feet, and the same size is maintained up till 18 feet above high water, from which point they begin again at 70 feet by 40 feet, and diminish to 50 feet by 25 feet at rail level, above which they rise 50 feet. All the piers were of Aberdeen granite outside and of sandstone within. Connection from end to end of the viaduct was achieved in October, 1889, almost 7 years after the undertaking was commenced, and through passengers for the North from England can now, by availing themselves of it and the new Tay Bridge, reach Perth and the North Country an hour sooner than they formerly could. Besides the advantage in mileage gained by erecting the fourth bridge, the fact that it may be considered the greatest engineering marvel of the age will tend to draw passengers toward it in preference to the longer opposition route. One would expect that the traffic would need to be large to justify the expense of such leviathan bridges as those at Queen's Ferry and Dundee, and that it is, at certain seasons, immense, and well worth competing for. Anyone can realize who witnesses the commotion in one of the great London railway termini, or at Perth Station during the first half of August, when, besides the crowds of tourists, holiday seekers, and business men, the great annual migration northward of sportsmen, with their followers, horses, and dogs, takes place. The following figures relating to the bridge are rather interesting. The quantity of Siemens Martin steel used was 54,000 tons, of cement, 20,000 tons, of granite 707,000 cubic feet, of masonry and concrete, 117 cubic yards, and of timber, 1,000,000 cubic feet, chiefly used in constructing the jetty and preparatory works. The surface of steel which will have to be painted measures 20 acres fully. The number of men employed was at times as many as 5,000, and the deaths caused by accident averaged about 1 every 6 weeks since the work was begun, the total amounting to 56, which, though it seems high, cannot be wondered at considering the extremely hazardous nature of the work. Comparisons, though they may be odious, will inevitably be made in discussing the fourth bridge. As regards the length of the spans, it is easily first with 1,710 feet, being well seconded by the Brooklyn Bridge at New York with 1,600, the latter is, however, a suspension bridge. It is easily beaten in total length by, for example, Its next-door neighbor the Tay Bridge, which is 2¼ miles long, being 3/4 of a mile longer than the _Fourth Bridge. It is by far the highest bridge in the world, and, indeed, only 3 buildings of any kind overtop it: the spire of Cologne Cathedral, the Great Pyramid of Egypt, and the Eiffel Tower in Paris. The last mentioned is, however, not to be compared in audacity of conception, difficulty of execution, scientific interest, or practical utility to the Fourth Bridge, which holds in rigid extension between each pair of Herculean shoulders a length of steelwork nearly twice as long as the Eiffel Tower is high, and which, while delicately adjusted to allow of adaptation to the slightest change in the dimensions of its parts, is at the same time of strength so immense, that the weight of a couple of ponderous mineral trains passing along it at a distance of 850 feet from its nearest point of support can be treated as a matter of little moment, it being but a trifle compared with the ever-present strain necessary to maintain its own colossal form, and stand immovable under the furious attack of the hurricane. Having now described the work and workmanship of the Fourth Bridge, it only remains to name the masterminds who planned and erected it. The designers were Sir, then Mr. John Fowler, and Sir, then Mr. Benjamin Baker, the well-known civil engineers, and the contractors or builders were Messrs. Tancred, Errol, and Company, and it is only justice to say that it is in great measure owing to the many inventions of special methods and tools by Sir, then Mr. William Errol during the progress of the work, and, in general, to the extraordinary resource displayed